In this part of the polynomial lesson, we're going to focus on multiplicities. Multiplicities happened when a root occurred more than once, and that is also looking at a corresponding factor that is occurring more than once. So here's a function f of x. It's equal to x times x plus 3 squared times x minus 6 cubed. If I was finding the roots of this, we would set it equal to 0. And then we would set the factors equal to 0. Well, that first factor, x, equals 0. There's nothing to do. X is 0. So we have one root at 0. We have another one that's going to be at -3, but it has a multiplicity of 2. And then lastly, x minus 6 equals 0 means x equals 6 with a multiplicity of 3. So as far as the roots go, we had 1 at 0, and it was multiplicity of 1. We have 1 at -3, and it was multiplicity of 2. And 1 at 6, which was multiplicity of 3. Each of those multiplicities does a different thing to the graph. Now, if it was a multiplicity of 1, we're going to see it go straight through the root at that specific x-intercept. This one's going straight through 2, but it's going straight through the x-axis there. So a written description would say goes straight through the x-axis at that root. Goes straight through the x-axis at that root or 0, whichever one you want to call it. If it was an odd multiplicity, we're going to see this cubic-like behavior, or at least an odd degree-like behavior, because it's going to kind of wiggle or bend through the x-axis. It's not going directly through. It has this curvature to it, and that curvature is important. So we're going to say it bends. I like to say it wiggles. So it wiggles through the x-axis at that root. And then lastly, if that multiplicity is even, so if it was like multiplicity 2, multiplicity of 4, or so on, really we're going to focus on multiplicity 2 mostly. So that would bounce off the x-axis at that root. Just like a quadratic function does, like the parent function of a quadratic would bounce off the x-axis automatically. So we know this quadratic hits the x-axis, goes right back up. It's going to bounce right there at the 0, 0. Now, if I know the roots, we can write a polynomial based off of those roots. We just have to work backwards a little bit because we have previously written the roots from the factors. We can see that there's a relationship between them. Now we did do this with quadratics, so it's a little bit of a reminder, but I'm going to write these out separately. We've got x equals -6, x equals -1, and x equals 5. If we were to work backwards from that root and get it back to 0, I could do x plus 6 equals 0, and that's the factor. We see x plus 1 equals 0. There's going to be the factor. X minus 5 equals 0. There's the other factor. So our function could be written like y equals x plus 6, x plus 1, times x minus 5. For this polynomial, one thing that I'm going to explain in the next video is that there could actually be some value in front of this. Now this might be a vertical stretch or vertical shrink. Maybe that's a 1/2 where it's shrinking the values down, but if that doesn't have a variable with it, there's no way that it's creating another 0. It just happens to be some type of multiplier, some scalar, where it is either stretching or shrinking it. So there's actually an infinite number of polynomials that have these roots, but we're going to actually solve for A in a later video. If we were doing this next one, we have a 0 at 0. Well, x equals 0, there's nothing really to work out. X equals -2, I can move the 2 back over to make that x plus 2 equals 0. Now that factor is being revealed. X equals 7, I can move that 7 over by subtracting it, and x minus 7 equals 0. X equals 10, move the 10 over, x minus 10 equals 0. We see these factors start to come up, or well, they're going to create the factors. So one of them is x, one of them is x plus 2. We have an x minus 7 and an x minus 10. Again, there could be some type of multiplier, so I'm still going to write an a here. Maybe it's 2x squared, or 2x times x plus 2, and so on. But each of these are factors that are coming from a specific root, or 0. For the third one, there's a little bit more complexity to this. So I've given you some fractions for us to consider. X equals 3/4. If we were to work backwards, we could undo this division by multiplying the 4 over, so it would say 4x equals 3. We can also subtract that 3 over to make that 4x minus 3 equals 0. And that's the factor that we would have seen on that previous video. X equals -2/5. Again, we can undo that division by multiplying the 5 over, so 5x equals -2. Add the 2 to the other side, so 5x plus 2 equals 0. Look, we're already seeing these form some factors that we will use. X equals 8. Not much to move, but x minus 8 equals 0. The next one is a multiplicity. So it says x equals -3 that has a multiplicity of 2. Now the factor itself is coming from the root x equals -3. So if I move that 3 over, it's x plus 3 equals 0. This is still multiplicity of 2. And that's going to be important once we start creating that function. X equals 0, multiplicity of 3, there's nothing to move over, it's just x. X equals 0. So our function is going to start with this x cubed because there's really no x minus anything, it's just x. But there's multiplicity of 3, so it's x to the 3rd power. We can have this x plus 3. That's to the 2nd power because it's a multiplicity of 2. There's an x minus 8. Doesn't have a multiplicity, it's just to the 1st. A 5x plus 2. And a 4x minus 3. Again, there technically could be some type of constant out front, so I'm just going to write a times whatever that is. But these are all creating the factors from the specific root. What we'll see is that if x equals c is a root, and maybe you've already figured this out, then x minus c is a factor of that polynomial. And we're going to name that polynomial p of x.